Hello, everyone. My name is Ray Abazi, and I want to start off by thanking you for joining me in today's session. I'm going to be going over with you a method that we developed along with two inventions for the extraction of shoreline marine debris microplastics, the removal of or separation of natural and synthetic material, along with the results and figures we received from using these methods. So we know that there's a growing concern on marine debris pollution and microplastics, its impact that it's having on our ecosystem, and that a standardized process is needed for us to understand how much material is accumulating on our shores. It's believed to be over 24 trillion pieces of microplastics in the upper ocean, and current methods for us analyzing the shoreline marine debris, specifically microplastics, are not allowing us to view and quantify these smaller figures, and are also digesting the synthetic material along with that organic debris or that natural material, and not giving us the proper figures and results that we need to understand how much is washing on our shores. So these are the methods that we created. So starting off, we went to James Campbell National Wildlife Refuge. It's on the northeastern shore of Oahu and Kahuku. We selected a 40-meter wide beach and set up 3 separate transects. On those transects, we then placed our quadrant over the area with the highest level of marine debris, or on the rack line. The week prior to us coming out and placing these quadrants and doing this process, we cleaned the beach completely to give us a baseline for how much was there. We did, again, 3 samples. The quadrant is 1 meter square, and we were removing 1 inch of sand and debris from that quadrant, and was roughly 34.83 kilograms of debris that was being collected, and that was collected in 5-gallon buckets. Once we've collected that material, we are then pouring it into a buoyancy separation device, and the name explains what it is. We're just collecting ocean water, putting it into this system that is circulating that water through it. We have 2 pumps underneath that are sucking the water from the lower chamber, pumping it through the hoses. Those hoses are then used to percolate and agitate sand, floating up all of that material that is in our sample. That seawater is filtered through a 25 micron screen to prevent any cross-contamination. And we are doing this process for about 7 minutes, or until we no longer visibly see any buoyant particles coming to the top and flowing into the lower chamber. If you wish to learn more about this process, the QR code in the bottom right will take you to an animated video that helps demonstrate and explain how we are doing this. But again, we're just using the density of these polymers to float them out. Once we have all of these polymers floated to the top, we are then pouring that water and all of that debris into another clean 25 micron screen, labeling it, and then bringing it back to the lab. Along with that debris, we are also collecting the clean sand from each quadrant in a 1 liter container for us to further analyze if there's any material still left in that. So list of polymers on the right. Again, we're going to be looking at any polypropylene, polyethylene, ethyl vinyl acetate polymers, anything that is less than that of seawater, which here in Hawaii is around 1.023 grams per milliliter. And again, if you would like to learn more about it, there's a separate video. It's a live video showing how the BSD works and giving you a better demonstration. Once we bring that material back to the lab, we are then using a trash time machine, or a debris separation vacuum chamber, to separate that natural and synthetic material. It is just a basic vacuum chamber with a vacuum pump, and we are taking that debris that we've collected, we are flushing it into the vacuum chamber using deionized milli-Q water filtered down to 20 microns, putting all that material in the chamber, placing that screen on top to keep that material submerged, and then filling it with water. And then we are turning the vacuum pump on. As we pull air out of that chamber, we are also pulling it out of the pockets and cells of that natural debris. The porosity of natural material is much larger and abundant than that in the synthetic material. So as we pull the air out of that material, and once we release the pressure back into it, the material acts like a sponge and is going to pull all of that water into its pores and cells, force waterlogging that material in a matter of moments. This process is taking it's taking 20 minutes, and we are pulling down to 27.5 inches of mercury. And we're again now separating that material into its 2 separate chambers, where we have our floating synthetic material and our sinking natural material. So an upper and lower chamber, and we're just using that density difference of cellulose and water. And if you would like to learn more about the TTM, again, there's a QR code on the bottom right that will take you to it and you can learn more. After we've got that material separated, we are letting it air dry until we receive a constant mass. And then we are putting it into a 7-stack sieve, giving us 8 different chambers, which you can see there. For this process, we looked at the 5 millimeter, or the greater than 5 millimeter, the 1 to 5 millimeter category, and the 63 to 25 micron. Due to the abundant amount of particles that were in the other chambers and the time restraints that we had, we did not analyze the other compartments. And for the less than 25 micron, we lost 1 sample, so that's why we didn't go with the smallest. But we are sieve stacking and separating it for the floating chamber, the sinking chamber, again, natural or synthetic, and for that clean sand. So for the 5 millimeter class, from all 3 transect or quadrants, there was over 5,000 pieces. Of all those pieces, over 3,300 were synthetic, the remaining were natural. For our synthetic pieces, all of them were counted, photographed. We wrote down the colors, the type of material it was, its weather coding, its mass, and then we further analyzed subsample of this on the Thermo Fisher IS5 ATR FTIR. For the 5 to 1 millimeter category, you'll notice that 52% of that total mass was just in this chamber. So there was a significant amount of microplastics or micro debris in this. Again, all of these particles were photograph weighed, categorized by their color, type, weathering code, a subsample process by the Thermo Fisher IS5. In the clean sand, we found 5 pieces. Same metadata was taken from that. And then with the plant, we, beyond just visual identifying or visual confirmation that it's natural material, we threw it in the IS5 to make sure that it is cellulose and not a synthetic piece. For that 63 to 25 micron size range, we sent those samples to Agilent Technologies, where they use their 8700 LDIR to analyze these particles. Before we sent it out to Agilent, we used our Sartorius Micro N3P balance to give us an accurate balance of how much we're sending out to them. Of that sample that we sent out to Agilent was half of the total. Agilent then took a quarter of that sample, spent it in 5 milliliters of ethanol, sonicated it, and then took 10 microliters and added it to a slide for analysis, again, on that 8700 LDIR. And Agilent has a library group of 35 different polymers that they ran it against, along with calcium carbonate being added to it, and silica. So for that greater than 5 millimeter size category, we were able to identify 7 different polymers in that chamber, and analysis showed that 70% of them were white polyethylene fragments with a 2.3 weathering code and an average weight of 152 milligrams. Our mean quadrant polymer mass, so just synthetic material, just plastics that were in there, was 177 grams and over 1,000 plastic pieces. And that's the mean count again. There is 5.1 grams of plastic per kilogram of sand and 33 pieces. So again, these are just our larger pieces, our greater than 5 millimeter. This is our meso and macroplastics. We can see this figure in here that there was some natural material that did not get separated in the process, and also some plastics that sunk during this process, and we'll go over that later. For 5 to 1 millimeter, again, notice the mass difference, the particle difference, how much more abundant there was in degrees of microplastics compared to the larger plastics. 78% of them, again, white polyethylene fragments with a 2.3 weathering code and average weight of 9.58 milligrams. Our average quadrant counts. This is, again, a big one. This is how much was in each quadrant, close to 20,000 particles. Our average weight is 5.204 grams per kilogram of sand. That's greater, again, than what our meso and macroplastics were. With each kilogram or almost handful of sand, or 2 handfuls, you're getting about 561 pieces in there. So we have 2 additional polymers that were found in this size category compared to the other. And again, some plastics that sunk in that process, again, a very small amount, and some natural material that didn't sink in that process. In our much smaller size category that was sent out to Agilent, they were able to collect over 6,600 spectras, and our mean quadrant polymer mass that we removed before we sent out to them of those plastics was 93 milligrams. And the mean amount of plastics, these polymers that was in each quadrant, was over 1.6 million pieces of these microplastics. It's a very, very startling figure. That's the extrapolated data from what Agilent processed, and per kilogram of sand, again, 46,000 pieces. You notice in this one that there was more material than the other 2 chambers as far as what was separated natural and synthetic wise, but still very good results using this process. For the sand that we sampled and sent out to them, there's 255 spectra collected. Of all of the sand that they analyzed, there was only 2 synthetic polymers found, an alkali varnish and polyethylene. Everything else was carbonates. So very good results from the buoyancy separator device, removing this material from the sand. So with the buoyancy separation device, again, this is an open source tool that we created to allow anyone to be able to remove this material. So it's great for its practical application in cleaning up our beaches, but also an effective tool for us analyzing scientifically shoreline marine debris pollution. From using this method, we found that it is 99.99% effective at removing this material, and that per quadrant, we're removing, again, over 1.6 million pieces in this process, and that on Oahu shores, 55% of our mass is just microplastics. The BSD captured 11 different polymers, and of all synthetic material that we removed, 12.36 grams of that material per kilogram of sand. Startling figures. The trash time machine worked very well at retaining plastics. 99.5% of all microplastics in there were able to be retained using this process, and 91% of that natural debris was able to be separated. There's no chemicals being used in this process. It's just water. It's just negative pressure. It's a very simple, easy way for us to separate that material and analyze what is, again, washing upon our shores. So for the trash time machine, everything greater than 1 millimeter in dry mass, over 20,000 particles, this is mean, per quadrant that was removed. Separated, again, 90% of that natural, 99% of synthetics. From Agilent's counts, still good figures. We believe that the sinking of these synthetic polymers is due to the density difference of salt water and the deionized water. Experimental results are showing that that is the reason, but further analysis needs to be done. But trash time machine works very well. So in conclusion, again, going over everything with you, 83% of that material that we removed from our BSD or from our beaches was synthetic, was plastics. The BSD had a 99.99% efficiency of removing microplastics down to 25 microns and larger. In this quadrant, per quadrant, there was 1.6 million pieces or more in that chamber. That equivalates, when we extrapolate to the 40-meter beach, to being over 65 million microplastics, or 758 water bottles. In mean concentration, there's 0.52% of microplastics in our beaches, or 1.02% of marine debris on our shores. That's all plastics. And it's much better than using acidic digestion. It's, again, just water. It's very easy. Would like to thank everyone from Center for Marine Debris Research, Hawaii Pacific University, U.S. Fish and Wildlife, Thermo Fisher for their technologies, and Agilent. Please pause this, check out the other presentations that we have going on during OSM 2022. And thank you all for taking the time to listen.